All right, so let's work through example number 6 from the student note packet. Okay, you'll notice that we have a couple of blocks here. They're attached by a string in the middle. Okay, we're going to assume that this is our magical physics string that's massless and, doesn't cause any extra loss of energy or anything like that. So just a magical physics string there connecting the two. And then we've got an extra string that's connected to the floor, which is exerting a 100 Newton force in that direction. All right, over to the right. Okay, so we're going to hopefully find the acceleration here. Now I'm going to work this in two different ways. The first way is just going through what we would normally do to show that you could still do it. Also to introduce you to the idea that, yeah, sometimes things mathematically can be a little more complex. Then I'm going to work through it a second way which is going to be slightly easier, but only if we recognize it as such. All right? So here we go. First method, this is obviously, we've got forces, we've got tensions. We're looking at Newton's second law here, right? So let's go ahead and Newton's second law, we're going to draw free body diagrams. That's the first thing that we do is to draw free body diagrams. So first I'm going to do the 6 kilogram block right here. And hopefully you're recognizing that number one, it's got gravity pulling down. It's got the normal force of the ground pushing up of the table. Okay, so force of gravity, and then the normal force of the table pushing up. It is connected to this tension right here, which is pulling it to the right. So I'm going to just label that as a T, which is pulling over to the right. And that's it. We said at the beginning, if you read up here, it says it's smooth. The surface is smooth, which means that it's frictionless. Anytime that we say it's smooth, then we'll go ahead and ignore friction. We'll get to some questions later, not today, but at some later point where we start to look at some more difficult questions that involve friction as well. But let's start off without. So we've got all the forces there. I started with the 6 kilogram, just kind of no reason. It's just on the left. It was the first one I came to. I also noticed that there's less going on there, so I'm hoping maybe I'll be able to do some stuff without having to do some, go through more extra mathematics. All right, so here we go. If I do the sum of the forces on this, I can do the sum of the forces vertically, which is that the normal force of the table, there's only one, so I'm okay just labeling this normal force. The normal force plus the force of gravity, sum of the forces, is equal to the mass times the acceleration. Now, of course, the mass here, the acceleration here is 0, so those two add up to 0, which is something that we already knew. We knew that the vertical forces are going to have the same magnitude, right? They have to have the same magnitude so that it doesn't go flying off the table or sinking down into the table. Okay, so it only has horizontal acceleration here. So the vertical stuff is going to cancel out. So now I'm going to do the horizontal, and the only force there is tension. There's no other horizontal forces since there's no friction. Now because of that, that means the tension to the right is equal to the mass times acceleration. Now I do know the mass, right? The mass of this block is 6 kilograms. So I can put that in, but unfortunately I don't know this tension. This tension is this one right here. I'm going to end up labeling this one as T2 later, but I don't know what this tension is. And so I can't put in a number, and so I can't solve for acceleration here. So what we're going to do is we're going to go ahead and we're going to look at the other side. Okay, we're going to look at the 4 kilogram. Maybe we'll be able to do something with that. Or maybe not. We'll see what happens. So we'll go, here's my 4 kilogram block. Okay, again, it still has gravity. So I've got the force of gravity. I've got the normal force of the table. Now, if you want, you can label these, recognizing that these are different. Okay, you can label them. You can say, well, this is the force of gravity on the 6 kilogram block. This is the normal force of the table on the 6 kilogram block. You can just add to that subscript, and you'll see that a lot of times where it says this force is the force of this on this. And that helps us to differentiate when we start to do the equations and things like that. Are these different variables, or are these the same? So this would be the normal force of the 6 kilogram and the gravitational force on the, that is not a 6. It is a 6. It's just upside down on the 6 kilogram. All right. Now, continue with this force diagram. That would be the force of gravity on the 4 kilogram and the normal force of the table on the 4 kilograms. So we just add more to the label. Now we look at the horizontal forces. We still don't have friction, but we notice that there are cables on both sides. There's some tension on both sides of this 4 kilogram. So I have the tension pulling back this way, and I have the 100 newtons, which is that T2. You can either label it as T2 or as 100 newtons, going over to the right. Now, one of the things I'm going to do right now, because I can, is recognizing that these two tensions are the same tension, right? They're both from this same string here. Now, because that's the case, these two should have the same value. However, this tension is going to the right, and this tension is going over to the left. So I'm actually going to label this right now, just so I don't get confused later, as negative, because I want to make sure that whatever value I get for the t here, I get the same value for this t, but in the negative, the left direction, okay? So now I should be able to write my equations, right? I do the vertical first, and I recognize that the normal force on 4 plus the gravitational force on 4 is going to be equal to the mass times acceleration, which again, that acceleration is 0 because it's not accelerating up or down. All right, and then we do the same thing for the horizontal forces. Okay, we're going to go negative t plus t2 is equal to the mass, which I do know the mass. I'm going to go ahead and put the mass in, times the acceleration. Now, we also know t2, right? So I'm going to go ahead and take out the t2. We had actually already identified it as being 100 newtons. So at this point, we've got negative t plus 100 equals 4a. Now, you may notice, yeah, you got two variables again, Mr. Bywater. Yes, I do. However, this acceleration is the same for both blocks. They're both connected. They're both going to be moving at the same rate. Their speed is going to be changing exactly the same. And so we do have two a's, but they're both the same a. Same thing with the t, right? These are the same tension. It's the tension in this cable right here. And that tension is the one that it is the same for both of those. So we basically have two equations with two variables. You learned how to deal with that in Algebra 1. So you can use substitution, elimination. Probably the easiest way is just say, you know what, this 6a, I'm going to go ahead and substitute in for the t, which is going to give me negative 6a plus 100 equals 4a. And I'll leave the mathematics to you, but hopefully you get that the acceleration is 10 meters per second squared. And that's the answer to this question. We found the acceleration. Now, as promised, I do want to show you a second way to do it because the second way is a little bit quicker and easier if you can recognize it. Now, the second way is using what we call a system. All right, so I'm going to get rid of all of this stuff because it's not going to be important anymore. I could use it. Just because you didn't use it doesn't mean it's wrong. In fact, if I were writing on my own paper, I would not erase this. I'd leave it there, and then I'd go down to the bottom and do this other thing. Or maybe I started with that and I write these on later. Just because there may be other things that we need to find. If you want to find tension, you are going to need to write those equations. All right? But here, if we consider what we call a system is when we group objects together. Because in a system, the internal forces are not important. They don't affect the object. Okay, we've talked about before in class how when you have a single object in outer space, it cannot accelerate itself. It either has to push off of an outside object. Of course, Newton's third law says if I push on that wall, the wall pushes on me, so I get acceleration. Or I have to throw a ball. Similarly, if I push the ball by throwing on it, it pushes right back at me. And so I get some acceleration. But those are external. Those are things outside of the system. Okay? So here, I'm going to consider the system to be both of the blocks and the tension in between them. I don't need the tension in between them. That's not what the question is asking for. It's just asking for the acceleration. Okay? Now, if I do a force diagram or free body diagram on the system, I do know that it's 10 kilograms. Right? That's the whole mass of the system. We said that our string was massless, that magical physics string, so we don't need to worry about that. We add those together, we get 10.0 kilograms, right, for our mass. Then we have the force of gravity, we have the normal force of the table. And then horizontally, the only thing that we have is that tension, which is 100 newtons. And you can probably already kind of picture in your mind what this is going to do. Again, the vertical equation is just going to be those two together. It's going to equal 0. It's not helpful right now. But I can say that the sum of the forces equals mass times acceleration. So the sum of the forces here is just the tension pulling to the right equals the mass, which is 10, times the acceleration. And that tension, of course, is 100 newtons. So I just go 100 equals 10A, and I get, divided by 10, that 10 meters per second squared is my acceleration. Ta-da! How about them apples, eh? So anyway, we worked through this example. Hopefully that makes sense and that it's helpful in dealing with either individual objects or as a system. There are questions that are designed to force you to work with individual objects. There are also questions such as this one, which are obviously simpler if you consider it as a system. So we'll look at a couple more of those as we go forward, and hopefully that is helpful to you.